Guys, this video is over the gas laws. This is a review of chem. This is kind of where we start. Here we go. Got to be able to find your way around the periodic table. All of the elements are arranged by atomic number, which has to do with number of protons essentially. So you have atomic mass, atomic number, know what these things are. This doesn't have to take a lot of time. What is a mole? It's a little creature that burrows through my front and backyards, and they are a problem. The mole is just an amount of stuff, an amount of something, and you have to be able to convert back and forth. The mole is tied to this thing called Avogadro's number, or avocado's number, as I like to say it, and you can go back and forth from atomic mass, Avogadro's number, or liters of a gas. Have some knowledge of what a mole is. Can you convert? Here's some practice. You can pause and see if you get these. See if I've done them right. Hopefully I've done these correctly. Alright, we're talking about a gas, and we can talk about in a minute the gases that we talk about in this course. The factors that will affect a gas, the quantity of a gas, is usually measured in moles, that is in the temperature of a gas, pressure, and volume. We've already talked a bit about how to calculate pressure, how does volume fit in there. So these are the things that will affect our gas. In this course, gases tend to be ideal. They're perfect. Physics land gases. Okay. We have a bunch of different gas laws. So we're just going to run through them real quickly. First one's called Boyle's law. Pressure of a gas is inversely related to the volume. And so we keep certain things constant. Moles, so amount of stuff, and temperature is going to be constant. And this is the law. There you go. P initial times V initial equals P final times V final. Okay. Boyle's law. Second one's called Charles' law. The volume of a gas is directly related to the temperature of that gas. So now we keep different things constant. So now the pressure and the number of moles, the stuff, are kept constant. And here is Charles' law. Okay. Gay-Lussac's law, Gay-Lussac's law, however you want to say that. This time we keep moles and volume are constant, and the things that are changing, pressure and temperature. And so which one you use depends on what variables you're given in the problem, what's being kept constant, what's changing, and you should probably have these written down somewhere. I would, so I'd pause here or rewind and watch again. Gas law number 4, Avogadro's law. And finally, something called the combined gas law. You basically take 3 of them, put them together. Moles stay constant, so they're not in there. PV over T equals PV over T. And so typically the way problems work is that you're given certain things, you're trying to find one unknown, right? So here's a problem. The problem with problems in general is that they don't tell you which law to use, so you will have to decide, what do I have? What's given in the problem? What can I use to solve this? I've done all my math right. Hopefully I have. Have no fear, one of you will tell me if my math is wrong. And then finally, the ideal gas law. This is the one that we use, I think, most often. and I refer to this one as PivNert. I think most teachers do. PivNert. All the factors contribute now, so we're not keeping any one thing constant. And then we use something called R, which is our proportionality constant. This number changes depending on the units used. So you're going to have to look, see what units are used in the problem, because there are actually different R's depending on whether or not they use these or different units. So this is a thing. Here's an example. Helium balloon, and it sounds like a buoyancy problem. And they give you certain constants, and they give you certain things. You have room temperature. Oftentimes they'll give you temperature in Celsius, and you have to convert to Kelvin, because all of these dang rules use Kelvin. That's what the T is. It's in Kelvin. So you have to know how to convert from Celsius to Kelvin. That's one of the things you have to be able to do. They're assuming that the balloon is a perfect sphere, and so the volume of a sphere is 4/3 pi r cubed. And they give you the radius, which is very nice. They tell you its internal pressure, and you're trying to calculate something. If I've done all my math right, we can plug all that into the gas law. We're looking for number of moles. What is temperature? We'll be able to define temp. Temperature is a measure of the average kinetic energy of particles of something, typically liquids or gases. Most of the time we're talking about gases. So your temperature is a product of the average speed of all of your molecules. Now what happens here is that all the different molecules are probably moving at different speeds all the time, and so the thing is we have to take some sort of an average. We have to take an average in order to figure out what is the temp. Temperature only depends on the speed. So if you have a bucket of water or a small cup and they both have the same temperature water, that means they both have the same temp. Mass doesn't matter. Now compare that to thermal energy. This has to do with the average kinetic energy and the mass of things. So if you have more mass, you're going to have more thermal energy. So in this case, our bucket of water from the last slide has more thermal energy, even though it's the same temperature, because it has more mass. There you go. Okay, we're going to talk a little bit about kinetic molecular theory here. Okay, so where does pressure come from? Well, it comes from molecules of a gas or a liquid that are moving. Okay, and unless you are at absolute zero, your molecules are moving. And we have these 5 different things, and you can read them. Okay. So the molecules are treated as little point masses, and they collide with each other and the walls of whatever container that they are in, and the collisions are assumed to be elastic. And this matters for how gases work, and frankly how chemistry works. I want to show you an example. So here we have a box. The box is filled with an ideal gas, some gas, and all we're going to do is look at one particle, one little particle of that gas. And so I've shown that to you right here as a little sphere. It has a mass and it has some average speed, and it's headed towards the wall, and it will bounce off the wall. We're assuming that it is a point-like particle. The collisions are all elastic. If you remember back from AP1 what that means. Elastic collisions. Kinetic energy is conserved. And there are no interparticle field forces, so they're not pulling on each other in any sort of way. Now, we're going to start here. We're going to say what happens. Well, when this particle is moving, and it will exert a force on this wall, right? And so because it has mass and it has velocity, that means it's got something called momentum. It's got momentum. So as it's moving towards here, it's moving towards this wall, it has an initial, call that PI, initial momentum, which is mv, right? Mass times velocity. It'll bounce off the wall going the other way. It's an elastic collision. which means that the only thing that's changed is direction. So we have this little minus sign. Now, what is our change in momentum? So our change in momentum is final minus initial. So I take negative mv minus mv. Now, I will have students that will tell me, well, if you take negative mv and subtract mv, you get nothing. And that is not the case. What do you get? So you get a change in momentum that is negative 2 mv, right? That's what you get. Now, where am I going with this? What is delta P? So delta P is something called impulse. The two are related. Oh my gosh, this is all stuff from AP1. Impulse. Do you remember what impulse is? I'm trying to remember, Sharky. Impulse is a force times a change in time. So this hopefully is making sense. This little gas particle will exert a force on the wall for a short amount of time, right? And we can go from there, and so we can start doing math, okay? And so we can come up with this relationship here. This relationship says force times time. So what would our time be? And this gets a little crazy, right? Let's say that this distance here is called L, right? And we have it start, the gas particle starts here. It goes across, it hits, it comes back. That displacement would be 2L divided by the average velocity, and that is time. Wait, where did this come from, Sharky? This equation is V equals D over T. The distance traveled is 2L, right, down and back. The velocity is just this, whatever this average is, and I solve for T. So I rearrange this, solve for T, and I get this thing right here. Now, so if I solve for the force, this force here, I have to divide both sides by time. So I have my impulse, and I take this business and chuck it in there, and I get this equation for my average force. Now this is where I lose folks. This is when I start to lose people. And there's a whole lot of mathematics that happens. And there will be people who tell you, that it matters. I don't know that in a few weeks you're going to remember any of this stuff. I don't know. But I'm just going to cut to the chase. Okay, we're going to do a bunch of math. We started with this little particle headed toward a wall and it bounced off. Okay? Where do we end up? I'm going to keep doing things. I'm not going to show you because it really doesn't matter. But if we keep going from this situation, here's where we end up. After go through all the math, we end up with this equation right here, which if you look very closely, this equation is PIV-NERT. PIV-NERT, this idea of gases exerting pressure, all starts from momentum and the forces that occur when these little particles hit walls or hit each other. So imagine there are a gazillion of these little particles, and now you start to see where this whole kinetic theory of things comes from. So we have a whole bunch of these guys. Then you see how pressure happens and how we can use all these gas laws to talk about the effects of a gas on particular things or on containers or what have you. Okay, and so this is the idea behind kinetic molecular theory, and it's grounded in all the stuff you learned in AP1. Okay, last thing here. The higher the temperature, the more kinetic energy, right? The faster that all these little particles move. We can only take an average because there's so many particles and they're all moving at slightly different speeds, and so this idea of an average kinetic energy is 3/2 times small k times T. T is temperature in Kelvin. This K is called the Boltzmann's constant. And so we can calculate the speeds of these guys using this equation. This is square root of 3kT divided by m. I think the important things are really these points right here to understand about how pressure comes about from the individual particles. So I hope this has helped to make sense of this idea of kinetic theory.